Integration by substitution, one of the antiderivative techniques. This is undoing your chain rule. So we're essentially unchain ruling with this. So we're using substitution to get these antiderivatives. Okay, when you're doing substitution, what you want to identify is an inside and the inside's derivative, because this is we're doing the chain rule backwards. So when I look at a problem like this one, I see x cubed minus 2, and I know that the derivative of x cubed minus 2 is 3x squared. Well, there's a 5x squared out here, which is pretty close to 3x squared. It's a 5, not a 3, but we can fix that. So I think this one is going to work out. First thing I'm going to do is actually change the problem ever so slightly. 5 is a constant. And with constants, it's 5 times x squared times the square root stuff. There is no addition in here. There is under the radical, but that doesn't affect this property. I can actually pull that constant 5 out front and turn this problem into 5 times the antiderivative of x squared. And then I'm going to go really crazy. I'm going to change x cubed minus 2 to have an exponent of 1/2. Okay, now I'm ready to do my substitution. Like I said earlier, I see an inside, which is x cubed minus 2, so I'm going to let that be my u. You want to choose the inside as your u, and then you find the derivative of u. So the derivative of u with respect to x is 3x squared, except I'm not going to write du dx. I'm going to multiply both sides by dx, and if I multiply both sides by dx, that gives me a du. See, my dx's cancel. That gives me a du of 3x squared dx. Your du really is what determines whether or not substitution will work. You have to see your du. I see my du is 3x squared dx. I have an x squared dx. All I'm missing is the 3, and if all you're missing is a constant, that's not a problem. What I will do is I will simply put a 3 in the problem. Voila! Now I have my 3x squared dx, and I can do substitution. The problem is I can't just change my original problem like this. I've multiplied by 3 to make this work, so I'm going to offset that times 3 by multiplying on the outside by 1/3. So now I have 1/3 times 3, which is 1, so I really haven't changed the problem, I've just changed the way it looks. So let's go on with the substitution, and I'm going to substitute out some stuff. What's on the outside doesn't change. So this 5 times 1/3 on the outside of the integral is going to stay there. I'm going to write it as 5/3. Maybe that was an ugly integral sign. Let's try that again. That's a little better. All right, now 3x squared dx, all of that is my du. So I'm going to take out 3x squared dx. That's my du. On the inside, x cubed minus 2 is my u. So instead of x cubed minus 2 to the 1/2, I'm going to have u to the 1/2. And now this is the purpose or the intent of substitution, is to take what was an ugly antiderivative and turn it into something sexy that we can deal with. And I can do the antiderivative of u to the 1/2. I will simply add 1 to my old exponent, make it 2/3, and then I will divide by 2/3, which is the same as multiplying by 3/2. Just don't forget there is a 5/3 hanging out right there that needs to come along for the ride. So it's 5/3 times that plus a c, and now we've done the antiderivative. And once you do the antiderivative, you lose the little squiggly s thing and the du. You don't keep it once you do the antiderivative. There is a little bit of canceling I can do here, and it's just staring me in the face, begging to be canceled, so I will do this. I'm canceling those 3's, so that leaves me with 5 times u, but at this point we have to plug our u back in. We started with x's, we better end with x's. So instead of u to the 2/3, I'm going to change it back to x cubed minus 2, all to the 2/3, all over 2, plus c, and that is our antiderivative for this function. Good, good? You're good? Identify an inside, see if the derivative is visible, and then do the substitution. Let's try this one, e to the 5x. Now, e functions, for some reason, just scare the bejesus out of everybody. Nobody likes them. One problem with e is there's not a clear, defined inside like there was with this problem. I see that square root, and the x cubed minus 2 is clearly inside the square root. The e is not as obvious, but there is an inside, and the inside here is actually the 5x. It's e to that power, that 5x is inside the exponent. So that's what I'm going to try for my u. Whatever is inside is my first attempt at my u. So my u is 5x. Then I'm going to do the derivative of that. And when I do the derivative of 5x, when I do the derivative of this u, I don't look at my original problem. As a matter of fact, I'm going to pretend it's not there, and I'm simply going to do the derivative of 5x. So the derivative of 5x, the derivative of u, is going to be just 5, and I'm going to go ahead and move my dx over. So du is 5 dx, and then once I do the derivative of u, now I'll look back at my problem, and I'll look and see, is there a 5 dx in my problem? Well, let's see. I do see the dx. So I'm looking for 5 dx. I do see the dx. All I'm missing is the 5. And if you're missing a constant, which 5 is a constant, then that's okay. I can fix that by simply putting a 5 in the problem. But remember, if you change the problem, you have to offset it with a 1/5. And now I'm ready to do my substitution. The 1/5 on the outside comes along for the ride. Antiderivative of, let's see, the 5 dx, that comes out and becomes my du. And then I have e to the 5x, but 5x is what we called u. So instead of e to the 5x, I'm going to say e to the u, and I'll do the antiderivative of that. The antiderivative of e to the u is simply e to the u plus the c. Remember that 1/5 on the outside comes along for the ride. And then finally, you simply plug your 5x back in for the u. So our final answer is going to be 1/5 e to the 5x. And don't forget your plus c. Good, good? Good, 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 good. All right, let's see. Sine x over cosine x plus 8. Okay, we've got to pick a u and a u prime. This is not an easy antiderivative that I recognize. Now this one can be tricky because I know that I see a sine and I see a cosine, and I know that if I tried to let u be sine x, the derivative of u would be cosine x dx. Yeah. Which is okay for u. I could substitute my u in for sine x, but I don't see a cosine x dx. The cosine has to be multiplied by dx. I have a cosine down here, but the problem is I'm adding an 8 to it, and this cosine is in the denominator. This is, my du should have cosine in the numerator times the dx. So that substitution failed. I could not find my derivative of cosine, cosine x dx in my problem. So I erase that and I try again. The next thing I'm going to try, and this is another one where the inside is not painfully obvious, but in this case my inside is my denominator. So I'm going to see what happens if I let u equal my denominator, cosine x plus 8. Let's see, cosine x, the derivative of cosine is negative sine dx. And I look at my problem, and I think, okay, is negative sine x dx in my problem? Let's see, I have sine x, I have times dx right here. All I'm missing is the negative. So I can fix that by throwing a negative in my problem. But if I put a negative here, I have to offset it. So I'm going to put a negative outside. And this right here becomes my du. So I now see my du, which means I'm ready to move on with my substitution. Cosine x plus 8 in the denominator, that's my u. And so this problem will turn into, when I substitute, the negative on the outside comes along for the ride. Negative sine x dx is my du, and I like to stick that off to the side. So I have a fraction, and my bottom cosine x plus 8 is u. And since I substituted everything out in the numerator, I'll just put a 1. So I need to do the antiderivative of 1 over u, which that's the derivative of ln. 1 over u, the antiderivative is ln of u plus c. And this is something we haven't talked about yet, but when you do antiderivatives and you get ln as an answer, you need to put your inside in absolute values. And the reason we do that is simply to eliminate the possibility that u is negative, because you cannot take the ln of a negative. So we stick it in absolute values just to make sure that if we do have a negative in there, the function still works. One more step, I need to take out my u and plug cosine x plus 8 back in. There we go. Good, 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 good. Identify u and its derivative, and then you go on with your substitution. Okay, let's try, ooh, blank page, blank page! Nah, I don't feel like drawing a triangle, man. All right. Let's see, cosine x over 1 plus sine squared x. Okay, this one looks a lot like the one we just did. I generally, if I'm going to do substitution, I generally look in the denominator first, and my first attempt is to let my denominator be u, and I hope that works. So I'm going to try u equaling 1 plus sine squared x. And then when I do my du, I ignore my problem. Don't get distracted by what's in the problem. So I'm going to hide the problem. Whoa, I hid the whole thing. That was stupid. Let's pull this up. What's going on here? Whoa. Let's see. Let's keep pulling that. Oh, there we go. All right. So I'm going to ignore my function, and I'm going to find the derivative of this. Let's see. So du is going to be, let's see, 1 plus sine squared. That's the same thing as 1 plus sine x all squared. The derivative of 1 goes away, but this is a chain rule. So I'll bring down the 2. That'll leave me with sine x to the first. And then the derivative of the inside is cosine x. All right, so I have my du now. Oops, times dx. Then now that I've found my derivative of u, I'll look back at my integral. Do I see 2 sine x cosine x dx in the problem? Well, let's see. There is a cosine x, there is a dx, there is a cosine x, there is a dx. I can put a 2 here because I'm missing the 2 also. What I cannot do is put a sign. This is against the rules. You cannot put a variable in and then try to offset it on the outside. I wish that worked. That would make these problems a lot easier if that followed the rules set forth by the Math League of America, but it does not. So we actually cannot do that, which means this substitution won't work. I do not have my du in the problem, so that means I need to erase this, and we're going to start over. We need to pick something else for u. And your du, any derivative that you see, really determines what you pick for u. And what I'm looking at is this cosine in the numerator. In my mind, I'm looking at that, and I know that the derivative of sine x is equal to cosine x, right? And that's kind of what's playing around in the back of my mind. I know that the derivative of sine x is cosine x, so I'm going to see what happens if I let u be only sine x. Not sine squared or 1 plus sine squared. I'm only going to let u be sine x, and if I do that, the derivative of sine would be cosine x dx. And this is a problem where your du actually determines your u. In the other problems, I picked my u first. But in this case, I see cosine x, which is the derivative of sine, so that's how I chose du. And now I need cosine x dx, which I see right here as my du. So I can go forward with this substitution. So I'm going to carry this over here, and this will turn into the antiderivative. Cosine x dx, that's my du, so I'll stick that over here to the side. I have a fraction. I have 1 plus sine squared, so that's going to be 1 plus, and sine is my u. So instead of sine squared, it's going to be 1 plus u squared. And then I pulled that away, so that's going to be 1 over. So 1 over 1 plus u squared du, and we have to do the antiderivative of that. Okay, this antiderivative is either painfully easy or painfully difficult. There is no middle ground because you need to have that memorized. That is the derivative of arctangent of u. The derivative of arctan is 1 over 1 plus x squared. In this case, it's u. Don't forget the plus c. And then we simply plug our sine x back in. So our answer is going to be arctangent of the sine of x. So there's some substitution there. There's some substitution. Whatever you can find for du really determines the u. All right, let's move on. Let's see. X times 1 plus x to the 9th. I guess we do have the option of just expanding this out 9 times. That'd be a pain in the butt. If you know your binomial expansion theorem, that'll make it a little bit easier. But let's see. I see an inside of 1 plus x. So I'm going to see what happens if I let u be 1 plus x. Well, if that's my u, then my du, let's see. Geez, I forgot about that. Okay, come on up. If that's my u, the derivative of that, du is simply 1 dx. So the derivative of u is dx. And so I'll look back at my problem. Do I see my du? Let's see, du is dx. Well, yeah, there it is. It's right there. So that means I could go ahead and try the substitution. So I'm going to do my substitution here. This will be the antiderivative. Dx comes out, and that's my du. So I'll pull my dx out and plug in du. 1 plus x is my u, so instead of 1 plus x to the 9th, I have u to the 9th. Good, good? Good, good? The problem is I still have this x right here that I haven't substituted. So what I've still got left over is an x in this problem, which means I cannot do my integration just yet. This is a problem. When you decide to change from one variable to another, you have to wipe them all out. I've taken out this x, the 1 plus x squared. I've taken out the dx. I still have this x left over, so I have to find a way to substitute out that x to make this work. And when you're doing substitution, what you need to remember is substitution is strictly an algebra concept. It's nothing calculus. It's nothing crazy. We're simply taking out one thing and plugging in something else that's equal. So I'm looking here at this u equals 1 plus x, and I'm going to work my known magic here. If u is equal to 1 plus x, that means x would be equal to u minus 1. All I did is take that 1 and move it over to the other side of the equation. And if x equals u minus 1, then I can actually take that u minus 1 and I can shove it in for x right there. So this integral is going to become the antiderivative of u minus 1 times u to the 9th du. And now I finally have it strictly in terms of u, which was my goal, and we have to do this antiderivative. It looks difficult, but I'm going to work this crazy property known as distribution, and I'm going to distribute my u to the 9th through. Turn this into the antiderivative of u to the 10th minus u to the 9th du. I can do that. That's u to the 11th over 11 minus u to the 10th over 10 plus c, and then I'll plug my 1 plus x back in. So my final answer is 1 plus x to the 11th over 11 minus 1 plus x to the 10th over 10 plus some arbitrary constant. Good, good? Good, good? Good, good? Good, good? Good, good? All right, 2 more problems. How far are we? 18 minutes? Yeah, I kind of saw this one getting a little bit long. 2 more problems. These are definite integrals, so the idea behind the substitution is going to be the same. You don't tackle your limits of integration until you get to until you have an antiderivative. So I'm going to go through, and I'll do this kind of quick because this one actually sets up really nice. I have a u on the inside, so u is going to be 3 plus x squared. When I take the derivative of that, the derivative of x squared is 2x dx, and I actually have my du already in this problem ready to go. So I'm going to do my substitution. The 2x dx comes out as my du. My 3 plus x squared is u cubed, which gives me u to the 4th over 4. Now this is a definite integral. This is a definite integral. It's u to the 4th over 4 is our antiderivative. But we need to plug in our limits of integration. Do not get so excited when you have your antiderivative that you plug in 0 and 1 for u, because 0 and 1 were part of my problem, and those are values of x. 1 is an x value, 0 is an x value, so do not plug it in for u. I need to, in order to use 1 and 0, I need to plug 3 plus x squared back in, now I can plug in 0 and 1. Where you plug in the top one first, so 3 plus 1 is 1 squared, that'd be 4 to the 4th, all over 4. That's a lot of 4s. How exciting is that? Minus, plug in 0, that'd be 3 to the 4th, all over 4. And we're done. So make sure that if you plug in your original limits of integration, that you convert your problem back into terms of u. Notice I forgot my plus c, and that's because the constant is not needed for definite integrals. If you put the plus c in there, it would just subtract away on this step. And there's one more problem I wanted to do. Let's see, it's another definite integral, but I'm going to show you a little trick that might make it a little bit easier. I'll let you decide. Let's see, so I have 1 minus x squared. I'm going to let that be my u because it's on the inside. My du is going to be negative 2x dx. Let's see, do I have that? I have an x dx. I'm missing the negative 2. So let's put a negative 2 in here. We'll offset it with a negative 1/2. And that's going to give me negative 1/2 antiderivative. Negative 2x dx is my du. And that will be the square root of u, which will be u to the 1/2. So I'm just going to go ahead and change that to u to the 1/2. Now I'm going to do a little trick here that I think makes definite integrals a little bit easier. Notice these values, 1 and 0, those are values of x. I cannot plug in values of x when I have an integral in terms of u, but what I could do is convert my x's into u's. If x is equal to 0, then using this equation, u is going to equal 1 minus 0 squared, which is 1. So my x limit of 0 becomes a u value of 1. Hey, bell's ringing. And then if x is 1, that means my u is 1 minus x squared would be 1 minus 1 squared, which is 0. So I'm going to go from 1 to 0 of this integral. And now when I do the antiderivative, let's see, this is negative 1/2. I'm about to do the antiderivative, so I'll lose the little squiggle thing. And that would give me u to the 3/2 over 3/2, which is the same as times 2/3. And I will evaluate that from 1 to 0. I can go ahead and evaluate because I converted my x values into u values. So that gives me negative 1/2. And then 2 times 0 to the 3/2. I don't know what that is. We'll just leave it. That's kind of high-level math right there. Divided by 3. Minus, and then I'll plug in 1. 2 times 1 to the 3/2, all over 3. And there's our